For a lot of us, the word calculus probably brings back some not-so-fond memories of late-night cram sessions and a bunch of symbols that just don't make sense. But what if I told you that whole complex world was really built on just two pretty simple questions? We're not here to do a math test. We're here to decode one of the most powerful ideas humanity has ever come up with.
Yeah, I know. At first glance, this looks completely impenetrable, right? It feels like some kind of secret language. And you know what? In a way it is. But it's not a secret that's meant to be kept from you.
It's the language of change. Think about it. A planet's orbit, the way a disease spreads, the wild swings of the stock market. If something is moving or changing, calculus gives us the words, the grammar, to describe it with incredible precision.
Okay, so what's this language all about, really? Well, it turns out this entire massive field of thought was basically born from trying to answer two deceptively simple questions.
On one side, you have the right now problem, how fast is something changing in one single tiny instant, and on the other, you have the total problem. How do you add up a bunch of tiny little pieces to get a whole? For centuries, nobody thought these two things had anything to do with each other. So let's start with that first one.
To really get a feel for this first big question, let's just think about something we all know how to do: driving a car. I mean, if you drive 60 miles in 1 hour, that's easy, right? Your average speed is 60 miles per hour. But that doesn't tell you how fast you were going at the exact moment you passed that specific tree. So how in the world can you measure speed in an instant when literally no time has passed at all?
The tool calculus invented to solve this is called the derivative. And honestly, you can just think of it as a perfect, infinitely precise speedometer. It can tell you the rate of change of anything at any given instant.
And this idea goes way beyond just speed. Take a look at this table. It's showing the total depth of snow during a storm. Okay, so we can see how much snow is on the ground. But the more interesting question, the calculus question, is how fast was it snowing at exactly 9:15 a.m.? See, we're not looking for a total amount. We're looking for a rate.
Using the derivative, we can zoom right in on that single moment and find that instantaneous rate. It's a really powerful shift in thinking, isn't it? From asking how much to asking how fast.
But finding rates isn't the only trick up its sleeve. Derivatives also have this kind of superpower. They can find the absolute best or the worst outcome in any situation. This whole process is called optimization, and it's the math behind everything from planning the most efficient delivery routes to training artificial intelligence.
Check out this classic puzzle. A farmer wants to build the biggest possible pen for their animals, but they only have a set amount of fencing. I mean, they could make a really long, skinny pen or a short, wide one. There are so many options. How do they find the one perfect shape that gives them the most area?
Okay, here's the key insight, the aha moment. Imagine testing out all the different shapes. As you get closer and closer to the perfect one, the area gets bigger. But once you pass it, the area starts to shrink again. So, right at that absolute peak, the maximum possible area, the rate of change has to be 0, just for a split second. And by using the derivative to find exactly where that rate of change is 0, we find the perfect dimensions.
And when you solve it, bam! The answer is exactly 1,250 square feet. No guesswork. Calculus gives you the single best answer guaranteed. Pretty cool.
All right, let's switch gears. Time to move on to that second big question calculus answers. And on the surface, it seems like it has absolutely nothing to do with speedometers or fences. Finding the area of a square or a rectangle is easy. Length times width, we all learned that. But what about the area under a curve? When the edges aren't straight lines, our normal formulas just don't work. So how do you get a precise answer?
The solution calculus came up with is called the integral. And the idea is actually brilliant. You just slice that complicated, curvy shape into a huge number of incredibly thin little rectangles. Now, the area of each one of those tiny rectangles is super easy to find. The integral is just the tool that sums them all up to give you the exact total. It's like the ultimate summing machine.
Now hold on, don't worry about trying to understand any of these symbols. That's not the point. The point is that just like a carpenter has a bunch of different saws for different kinds of jobs, calculus has a whole toolkit of specialized techniques to solve all sorts of different area problems.
And this shows just how powerful that whole summing up idea really is. It can do way more than just find areas. It can actually be adapted to find the exact length of any winding, curvy line.
I mean, that feels almost like magic, but it's made possible by the integral. So, we have these two huge ideas: the derivative, which finds an instantaneous rate, and the integral, which finds a total sum. And for the longest time, people saw them as totally separate worlds. Until someone discovered a stunning, almost unbelievable connection between them.
And this really is the central mystery, isn't it? On one hand, you've got speedometers, measuring a single instant, and on the other, you're summing up an entire area. What could they possibly have in common? They seem completely unrelated.
The answer is one of the most beautiful and important discoveries in all of mathematics, the fundamental theorem of calculus. And here's what it proves: that these two operations, finding a rate and finding a total, are perfect inverses. They literally undo each other, just like multiplication and division do. It turns out they are two sides of the exact same coin.
Okay, so how does this actually help us? Well, take a look at this list of clues. Some of these facts are about the total value of something, like where a graph hits 0, and others are about the rate of change, where its slope is 0. How can we possibly turn this jumbled list of disconnected facts into one complete picture?
This is the connection. This is where it all comes together. The fundamental theorem is the bridge. It gives us the rules to take those individual facts about rates, the derivatives, and integrate them, weaving them together to build the entire, continuous picture. It connects the instantaneous to the total.
So in the end, calculus isn't just some dusty old subject from a textbook. It's a language. It gives us the power to describe the flowing, dynamic universe we live in, from the smallest particle to the biggest galaxy. It's a tool for asking better questions and, well, for finding better, more precise answers. So the only question left is, what will you describe with it?